Right, good morning. Today we're starting 4.2 and this section is about exponential functions. Okay, where do exponential functions happen? Here is a real life experience. I'm offering you a job, but you have two options for payment. Would you rather have $1 million after 1 month, or my second offer is, instead of $1 million after waiting 1 month, I will pay you 2 cents in the first day. In the second day, I will pay you 4 cents, and the third day I will pay you 8 cents. On the fourth day, I will pay you 16 cents. So every day I will double your salary. Okay? Which one would you take? Which one? The double. Yeah, because you've seen the table, right? But technically, if you pull somebody on the street and ask, oh, I'll give you $1 million after 1 month, or would you rather have 2 cents today and 4 cents tomorrow and doubled every day after 30 days? And everybody will take $1 million, right? But if you know a little bit of math, the power of doubling, which we call exponential growth, this is what exponential means. Exponential growth is huge. After the first week you start making $1, it's still not a lot of growth. And then after the second week your salary is $163. And third week you're making $20,000. It's still not much. But finally, in the last week, everything doubling. Remember, you start making in the last couple days, for example, $5 million, $10 million. And when you add these up, they make about $20 million you earn in a month rather than just 1 million. So it's 20 times stronger. How little you start with. That's why everybody is asking you to please save money right now so you can retire early. Because if you save a penny today and keep growing every year, hopefully the stock market does well, and if it keeps growing and exponentially, you will earn a lot of money when you retire, okay? This is the power of exponentials, but it can be, of course, opposites true. Sometimes you lose money. But assuming you have a successful investment, if you sooner you put some money away, the better the growth rate will be, okay? Hopefully, okay? So we experience exponential functions in investments, in anything growing actually, okay? Especially in farm science, plants actually grow exponentially. Yeah, in a week you see a tiny little seed grow into 10 times, right? Okay, now what is the formal definition of exponential functions though? Exponential functions are actually, it's clear from the title, exponents. They are things that have exponents around them, okay? So the exponent is the one that's changing, and base, there is a number on the base, it's constant. So exponential functions consist of a constant and a variable, but the variable is in the variable is in the exponent, the constant is on the base, opposite the power functions. Power function is this x to the b. What is the difference? You have the variable on the base, but the power is constant. So these two are different. This is what we call a polynomial or monomial. We have been seeing this x squared, x cubed, x to the fourth. These things look like exponential functions, but they are not, because variable is on the base is changing, the top remains the same. Again, exponential functions have base the same, top differs, changes, okay? So here are more examples. 3 to the x is an exponential function. How about 1 over 3? I mean, are we supposed to have big whole numbers all the time? No. This is a small number like 0.3333. It's exponential function as well. So the base can be any kind of number except 0, 1, or negative numbers. We do not like negative numbers on the base because if the power becomes 1 over 2, negative 4 raised to power 2 is the same as square root minus 4, and we don't know square root of negative numbers in real life, in real terms. It's a complex number, so it's undefined in real numbers. So we avoid negative base, no negative base. We avoid 1 in the base, and we avoid 0 as well. Anything else is fine. Again, why is this not an exponential function? Because base is not constant. Its variable is on the base. Why is this not exponential? Because it has a negative, and this is base 1. 1 to the x is always 1. This is always 1, so there is nothing changing. It's the constant function. It's not exponential. No growth or decay. Oh, by the way, we don't call it growth. I mean, this is growing 3 to the x. Like your salary is tripled every day. It's growth. Sometimes we call it, instead of exponential function, we call it growth function because you're growing, something growing. But if the base is a small number, if base is less than 1, like 1 over 3, it's actually called decay. Opposite of growth is decay. It's becoming less and less. Because when you square 1 over 3, it becomes 1 over 9. When you square 1 over 9, it becomes 1 over 81. It's even smaller and smaller. So the more the number on the top, the smaller that number on the base is, or the result is. So we call it decay. Does it make sense so far? Any questions on this page? Pretty simple. Okay, next step is sketching them. How do we sketch exponential functions? And the good news is you have 2 shapes. You need to pick one. Usually these functions get 2 shapes. One is, as I say, growth. It increases from left to right. You need to check left to right again. You climb up on it. It's what growth means. From left to right. First shape is left to right, growing because of 2 to the x. 2 is a big number. It's doubled every time you're doubling your salary. The second option is decay. The second picture is decay. Because when you go from left to right, your level is going down. You're sliding. So this is decay. Why? Because the number on the base is small. When I say small, I mean less than 1. So if you have a base number less than 1, look at the numbers. You start with 8, 4, 2. You're getting less and less. This is 0.125, 0.25, 0.5. The numbers are getting smaller and smaller. However, it never becomes negative. How small can these get? They can be very, 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 very small. Okay? But it will never be 0, never touches 0. It's a little bit shy of 0, above 0, but never 0 or under. How large can you grow? This side can go to infinity. Like you start with a small number, big, bigger, 2, 4, 8, huge numbers, 16, as you've seen in the previous table. You can go to millions and billions in 30 days or more. And eventually you will rise to infinity. This is going to infinity. This side is going to 0. Okay? Any questions so far? 2 shapes. Either the growth or decay. Alright. Let's take a look at our first question. I need you to graph this first. At first sight, what is your prediction? Is this a growth or decay? It's a growth because base is 6, more than 1, big number. Like your salary is 6 times more every day. Perfect. So I know I can predict the result already. I'm expecting a picture just like this. But I want to be precise. I want to take a couple of values and check out those values instead. Alright, this is a bad idea. Too much hassle. I will instead do hand key. So I will just take a table and construct several values so I can get much precise picture. So this is for x values and this is for g of x equals 6 to the x. Let's take some negative values like -2, -1 and 0, 1, 2 and positive values as well. When I plug in -2 I get 6 to the -2. How do I compute 6 to the -2? I know 6 squared, but I don't know how to do 6 to the -2. Do you know the trick? Wow, 6 squared is 6 times 6. How do I do 6 to the -2? You cannot compute negative exponents directly. You need to first make this exponent positive by taking reciprocal of it. When you take a reciprocal of a power, it turns into positive. Okay? So this is actually 1/36, and 1/36 is about a big 0.2 something. I need a calculator. Alright, 1/36. 0.27. Oh, I shouldn't be running this calculator. Mess up my computer. So I would rather use Google Calculator from now. This is about 0.27. If it is -1, it is 1/6, which is 0.16. If it is 0, it's 1. If it is 1, it's 6. If it is 2, 36, right? So let's plot these points. -2 and 0.27 is right here. -2 and 0.27. There's something wrong. This is 0.027, right? Right. So that, because I noticed that this is the first value is bigger than 16. It should be growth. So how did I drop the value? So I noticed my mistake. This is 2.027. So it's about here. The second one is at -1. It's at 0.016. A little higher. At 0, you're at 1. At 1, you're at 6. And at 2, I can't make that picture, but you know, up high somewhere on air, there's a value there. So just connect these and get a better picture than our initial estimate. Okay, it doesn't touch x-axis though. Alright, this is roughly what it is, but you're lucky on ConnectMath. They will present you several pictures, you just get to one. However, you need to describe the domain of this thing. When I say domain, you need to press this down and check out all x values. Oh, it looks like only from here to there. So it's from -2 to 1. Am I right? Now, imagine this is going indefinitely to the right and left. It's the entire x-axis is the domain of it. Domain is the set of all x values you can insert and the function will be computable. And it is entire x-axis. How about the range? The range is a little bit different. What do you think? For range, you need to compress this or smash this picture from the sides, both sides, and push it towards y-axis. Imagine y values. What is it?
0 to infinity without including 0.
Yeah. Including 0?
Without.
Without, yeah. Excluding 0, we go to infinity. Okay? Right? Look. You start without the 0 and go all the way up. Why? Because this purple picture never touches x-axis. No value on the ground. Okay? They want us to fill out this table. We already did. It's 1 over... Again, don't type in 0.027, my approximation. Okay? It won't like it. Put exact numbers. Express numbers. Okay, hold on. What does it say? And simplify. We're using integers or fractions. Don't use decimals because decimals are approximations. 1 over 36 is not a terminating number. So instead, just use fraction 1 over 36 we got. And this was 1 over 6. For plotting, decimals are great. 0.027, you know where is abouts of it. But for computations and for supplying answers, use fractions. At 0 it's 1, at 1 it's 6, and at 2 it was 36. Alright, now finally they will ask us to graph. And which one was the right answer? It was this. You only graph this portion of it, but it goes all the way to the left. You see, it's almost parallel or coinciding x-axis, but when you take a deeper look at here with a magnifying glass, there's a tiny bit hairline difference between this blue curve and the x-axis. So it's D. Okay. Alright, this is how you complete any graphing questions. They will basically ask domain, range, and pick the graph. I won't be doing second one on Connect Math, only in here. Alright, what do you think the picture will look like? Growth or decay?
Decay.
This time it's decay because this is a number less than 1. Less than 1. So this is a decay. We will go, so I can even do the picture quickly here. Yeah, not bad. But you're supposed to get this picture with a table of values. Let's also identify domain and range of this thing. What is the domain? Domain. Push this down. What's that?
Infinity.
Negative infinity to infinity. Actually, as a matter of fact, all basic exponential functions, unless they modify it somehow differently, has the same domain. All numbers. You can insert any x you wish, and it's always computable. Range is, for this one, press this down here. This is what you get, right? So it is from 0 to infinity. Simple. Any questions? Alright. Everything I said so far has been summarized on this table, so put this onto your note sheet. If your base is more than 1, you have a growth. If your base is less than 1, however, base can never go under 0 value. It has to be positive, but small, then it's a decay. Decay when b is small, when b is big, it's growth. And all the time standard exponential functions have domain as the entire real numbers, negative infinity to infinity. We have already experienced that in the first two questions. Range is as default from 0 to infinity. It's above x-axis, never touches 0, so we are shy of 0 and grow into infinities on the left or right. Okay, we didn't mention this, but since these lines or curves are approaching x-axis, you see they are hairline shy of x-axis. X-axis is kinda a global attractor for them. It attracts my curves. They go really close to it. We call this a horizontal what? Asymptote. Anytime your curves get closer to a horizontal line on the far right or left end, we call it asymptote, horizontal asymptote. Here we go. And this is significant. No matter what base you take here, 3, 1 over 3, 5, 1 over 3, 5, 6, 1 over 6, small or big, all these curves always cross y-axis at 0, 1. This is significant. Because when I enter 0, y-intercept means 0, x value is 0, b to the 0 is always 1. Isn't any base raised to the power 0 is 1? This is a fact. No matter what base you take, when I enter x into 0, 1, that's why all these curves are crossing y-axis at this specific point. How fast they grow or how fast they decay, they will always go visit this town or this point, this kind of intersection, meeting points of all the curves. Okay? This makes sense? You can all observe this from a single graph. Alright, we're just gonna do another graphing activity, but this time it's not a basic exponential function. Somebody greatly modified this function. What modifications they made? Let's take a look. Do you see some modifications made into a base function? This is the base function, standard. And somebody took off -4 from x, and finally they have removed a number, subtracted the number from the entire base function after the base function. So I bet these are something we have seen earlier, right? In section 2.6, transformation of functions. So what kind of transformations do they describe? Subtracting something from x only, but subtracting something from the entire function. There are two shifts here. What kind of shift is -4? This one. This is a right shift. How about this one?
Down.
It's down 1. Yep. A number subtracted from the end, like x squared -1. This is parabola. This is bringing it 1 down. But if you have subtraction from x under the square, this is right shift. Same deal here. I see 4 next to x, it's a right shift. I see 1 far apart on the end, it's a downshift. So we need to first start off with the standard equation by finding its values. We already did kind of with 3, right? Or 6. you're gonna do the same thing. So 2 to the minus 2 is 1 over 4. 1 over 2 squared, it's 0.25. This is 0.5. This is 1. This is 2. This is 4. You just fill out this table and make the graph of 2 to the x. So just plot these. Minus 2 at minus 2 you have 0.25 here. At minus 1 you have 0.5 there. At 0 you have 1. At 1 you have 2. At 2 you have 4. Here we are. Okay, this graph, however, belongs to 2 to the x. They want us to find out graph of this guy. So you're gonna shift this 2 right, 1 down. Alright, watch how I'm doing this. I'm gonna shift this 2 right, look, this point will go 1, 2. Start value will go 2 right. I did. And then 1 down. So it's going to go down here. It was at 0. Almost at here. It was a little bit shy of 0 here. Now it's going to go almost into minus 1. And I will make my final picture right here. It was a right shift, correct? Right and down shift. This is called 2 to the x minus, oh wait a minute, it's not 2 shift, it's right 4. Who said 2? I did, I think. So I have to shift this 2 more right. So 1, 2. Yeah, I have to shift this 2 more right. Alright, this is about it. Okay, I graphed it, but you're not just gonna graph it, you're gonna write its domain, and you're gonna find its range and asymptotes. Okay, I see one asymptote here. This is almost parallel to this line. It's almost touching it on the far left end. I'm wondering what this level is. What level is this? Y equals what? Anyone? How did you get that? Yeah. In regular standard line, 2 to the x has y equals 0 or x-axis as asymptote. But this one went down 1. So instead of getting closer to 0, this is going to get closer to -1. So I already did see it's equation of y asymptote is y equals -1. Next, domain. What is the domain of this thing? What is the domain? Oh, it looks like on this half. It starts here and goes all the way right, correct? Is it only here, domain? No, this line goes all the way to the left. Still, domain does not change. It's negative infinity to infinity. But the range change. Range is no longer 0 to infinity. It's not correct. 0 to infinity. Why? Take a look. It's almost touching here, and it's going up. So where is this starting value? -1 to infinity. It's no longer 0. So if there's a downward shift or up shift, your range change. Okay? So that's what you're gonna do in number 4. No, number 3. First, fill out this table. Okay. Alright. 1/4 this was, right? You can type in 1/4 or 0.25. This time decimal is safe because it's a terminating decimal. It's not like 1/3. 1/3 is not terminating. 1/4 is fine. You can write decimal if you, I think. I didn't check though. But I will be safe and still put it in fraction. 1/2, etc, etc. You know the deal. Okay, I don't want to do the rest of it, but it's very standard. Okay, can you handle it? Let me know if you have any problems with typing it in. Okay. Alright, next we are gonna take a look at a special exponential function. It's not a technically exponential function, this one, because it has a variable base. It has an exponent on the base, and on the exponent part is variable exponent, but the base has also variable, so I don't technically call this an exponential function, but it's an expression, involves exponential parts. Somebody took values of x bigger and bigger, like 100, and plugged in here 100 and 100 and took a calculator and computed it. 1000, they took a calculator and computed it. And 10,000, they put here 10,000 and 10,000 and computed it. And surprisingly, you expect to get bigger and bigger values. This is getting large, correct? You put a huge exponent like 1 billion here, but this thing is moving only a couple of digits on the far end. So it's pretty much, it's locked in the value of 2.7, and it's not really changing much. It's like stabilized into value. And with supercomputers now, they have computed maybe billions, trillions times trillions of powers, and they ended up that this number is always smaller than 3. It's about 2.7 something, and they called that value as E. So from now, when you see the letter E in an expression, just that number is a fixed number, but never terminating decimal, but it's fixed. It's not changing. It has so many digits in it, we can't count, so we shorten it with the letter E. Just like pi. Somebody was computing circle circumference and radius relation, and they found that ratio to be something like this, okay? And they called, since this has so many digits in it, it's waste of time to write all the time that so many digits. They have shortened it with this Greek letter pi. Now we do the same cheat. Since this has so many digits, we call it a letter E. But E and pi are just numbers, like 3 and 5 and 10. Okay? Alright? However, when you take this E in the base, because it's constant, we can take it on the base and raise it to power of x. This is a special exponential function for us. We call it a natural one. You will appreciate this function when you go to real calculus course and start differentiating it, because slope of this curve when you graph it is always equal to its y value at that value. So that's why it's natural. When you want to compute how fast this curve is rising, its slope, you just need to take a y value there and you're done. That's why I call it really natural. This number is not very natural to me. It's a weird number, but the slope of this function is great. Okay. So here is the picture of it. Because e is about 2.7, you expect a growth function, right? Because 2.7 is more than 1, right? We got a growth function, and it crosses y-axis at 1 again, as usual, because this is common to every exponential function. And somebody took some values and graphed it, thank you. And here is the picture of it, and please don't forget this picture. It will show up in calculus. This is very famous function, e to the x. So what is special about this function is nothing but the base. Base is about 2.77 something, okay? Never ending. Any questions on the picture? On e to the x? Natural exponential function is the name. Okay? Alright, just make sure this remains in our mind. Let's make an example, a problem about it. Okay. In the first step, first of all, do you see that this function g has been transformed from our famous exponential function e to the x? It's been transformed. I just want you to figure out what kind of transformation is this. There is a minus 6 involved. So it's a downshift. Is the downward shift by 6? It's a right shift again. Look, it's the same deal on this one. You had the x minus 4, now you have x minus 6. So it's a right shift 6. So what you need to do is plot the original one and then shift it 6 right. So to plot the original one, you need to fill out this data table, make those points, connect them, and get the picture of e to the x first. But I'm gonna cheat from this. Somebody already did it for us. So it's basically this one is what is asked here. Right, minus 2 is 0.135. But don't use 0.135 in connect math. Why? Because this is an approximation. Rounded off value. You need to enter here e to the minus 2, or in other words 1 over e squared is what you need to enter. I wonder if it's gonna like that. 1 over e shift 6 squared. Oh, it's gonna say incorrect because I didn't do the rest. Let's do this.
Actually, because I just did that and I had you put the decimals in there because I tried that and it didn't work.
Because I didn't read the statement. Yes. Look. Yes, you were right. It says round. Don't use this. Round your answers to 3 decimal places. So let's go with the statement. So this is what you need to enter. These values. Okay. But please do that with your own calculator. Don't just use the given values. Maybe they are wrong. I don't know. Okay. Once you sketch e to the x, this is e to the x, all we need to do is shift this 6 unit right. So I'm gonna take this point, for example, it's at 0, 1. When I shift the 6 unit right, it's gonna be 4, 5, 6. It's gonna be here. Okay? And just complete the rest of the picture from this. 6, right? Okay, makes sense? That's what you're gonna do in this activity. And domain and range. What is the domain of and range of this new one? Has it ever anything changed? Has anything changed from this one? No, still domain is negative infinity to infinity because we haven't shifted up or down, just right and left. Range is still the same, 0 to infinity as well. Okay, old one and new one both have the same domain and range. Alright, we learned the basics of exponential functions. You know everything about exponential functions. 4.2 is actually over right now, but looks like there is nothing fancy about these exponential functions as of now. Okay, they are just growth and decay going up and down curves, but what's significant about them is these are widely used in our real life. Really, very interesting applications. So in the next part, we're gonna see their applications into finance, banking. Okay, every day you put money into bank and it earns you interest, or you take a loan, mortgage, you pay some interest to them, and it's all computed by exponential functions. Okay, so our first topic, extremely important topic, is interest calculations. There are 3 formulas in banking business we use, but one of them is used 99% of the time. The other 2 rarely happens. If between friends you may use the other 2, but banking usually uses this one. What is the other 2? First one is simple interest. That means you put some money in 1 year or 5 years, but they don't compound the interest. I mean, at the end of the year, you don't collect interest and they don't deposit back to your account. 5 years, they give you just one block of interest. This is the formula when you see the word simple interest in the statement. That means no matter how long you keep your money, you just multiply your money with the rate, interest rate, and years. That's it. They don't, at the end of the year, you don't see interest. You see your interest end of the term, like 10 years, you get one block of interest. No compounding. Again, what are the letters here mean? This is the interest. I is an interest. P is the initial money you deposit. Or if you're taking a loan, it's the loan amount you take. R is, what is R? R is the first letter of rate, interest rate they offer to you. And T as in time, is how long you keep your money or how long you take a loan, what period of time. Usually it can be a month, it can be 30 years in mortgage. Okay, so they are used, the same letters are used there. Again, deposited amount, initial amount. This is the interest rate. This is the time in years, how long you keep. Oh, N is new here. N showed up first time here. N is how many times in a year you collect interest. Because there are some deposit accounts, they give you monthly interest. There are some deposit accounts, they give you interest every 3 months or quarter. There are some deposit accounts or loans you take, they charge you interest, or they pay you interest every 6 months. We call it semi-annually. Or there are accounts that give you yearly, like CD accounts, certificate of deposit, they pay you each year. So if it's yearly, your N is 1. If it's semi-annually or 6 months, so how many 6 months do you have in a year? 2. You get interest twice. Quarter, every 3 months you get interest. So how many times do you get interest in a year? 4. Monthly, if you're getting monthly, how many times do you get, these are n values, how many times do you get interest? Monthly, how many months in a year?
12.
Daily, you may get daily interest, or weekly, sometimes weekly, how many weeks?
52.
Daily? How about hourly? I deposit my money and take it back 1 hour later, they pay me interest. How many hours in a year? This is difficult. 24 times 365, right? About minutely, take it next minute back. 60 times, 24 times, you go compute, okay? How about secondly? How low can I go? It's 60, 60, 24, and 365. How about split second? Blink of an eye, I want my money back. Split second, I mean, it's so short of a time, you can't measure. I mean, it's a flash, okay? Momently. Then if it is momently, we cannot use n. We call it continuous compounding, and the formula changes to natural exponential function and simpler. And this is easy to remember. Spell this out or pronounce it. It reads like PERT. P-E-R-T, right? So if you are getting every split second continuously, no moment passed, we call it PERT, okay? And again, this doesn't happen in real life a lot. I mean, in banking, finance. This happens in biology and nuclear engineering, where radioactive material gets less every split second. You have a block of plutonium here, and every second in front of your eyes, it's getting less. You don't notice it, but it radiates some energy, and it decays. And this formula will come handy there, okay? We will revisit this, by the way, in the end of this chapter. There is a whole section about it. We'll go there and take a look. So this will wait until there. Banking, we don't really use it. Who wants his money suddenly back, right? With an interest. This is what often used. And simple interest, yeah, between friends, or if you know personal financing, you say, oh, here is 10 grand, give me 5% after 5 years. That kind of simple interest, you just multiply by 5, and then you compute your interest, okay? 5 years, 5%, P, 10,000, that's your interest. So again, in banking, we don't see these much. We use this. And the next question involves actually these formulas. Alright, let me clean this mess up. We need these formulas. In question 5, what we're gonna do is we are investing some money, 10 grand, right? At this rate, so let's mark these. These are all going into our computations. At this interest rate, 0.38, how long? 12 years you're keeping this money. But when do you see your interest back? After 12 years at once? No. They say there are options you pick. You can see your interest every year, or you can see your interest every 3 months, quarter, or every month, every day, or continuously. You can say stop and get your money out, and they will give you your interest at that moment with continuously. You need to first Tell me n values. I put them on the top earlier. For annually, what is n? 1. For quarterly, no? 4. Monthly, daily, they already supplied, and for continuous, we don't have it. It's infinity, actually. Alright, now we need to compute this. For annually, so you need to start with this formula and take it and use it for each 4 cases on the top. Last one is gonna be PERT. Okay? So take this formula, A P 1 plus R over N NT, right? Okay. Now I'm doing part A here. What is P? How much you deposited? 10,000. That's P. Alright, 1 is 1. We don't change it. What is R? Okay, this is interesting. Rate. How much? What's the rate they offered? Yeah. Don't put here 3.8. You need to turn that into, there is this sign next to it. That means, this means over 100. So you need to make this over 100, okay? This percent means 100, and change this into a decimal like this, 0.038. You just shift, add zeros, shift this 2 units to the left, 0.038. Okay, 2 units left because you are dividing by 2 zeros, 100. Alright, so I'm going to change this into .038. Actually, they should have said R is 3.8, and instead of N, they should have made 100 N. I mean, you kind of carry 100 here and 38 here. But anyways, it's confusing that way, maybe. Alright, what is N? N is 1 in annual, where I'm doing annual. N is 1. T is how long do we keep this money in the bank? 12. Okay, if you're doing manual without a calculator, hand calculation, you need to first do this operation. 0.38 over 1 is 0.38 again. 0.038. And then you need to add it to 1, which is 1.038. Then you need to raise it to the power of 12 and multiply by 10,000. Okay, at this stage I'm going to switch to my Google calculator and ask this guy what that number is. 10,000. 1 plus 1, nope, 0.038, right? Divided by 1. I'm just typing the whole thing. And raised to the power of 12. This is what it is, right? 10, 1 plus 0.038 divided by n, 1, raised to the power nt, which is 12. And voila. 15,644.736. Yeah. Alright, what is the rounding restriction? We need to round the answers to the nearest cent. Nearest cent is 73 cents. Is that right? Now look at the next number. If it's more than 5, round this to the up. Next number 74. I will use here this symbol because I have approximated it. Alright, that's what you're gonna enter right there. Alright, for n equals 4, you're just gonna go here and tweak couple of numbers. For n equals 4, this is 4. What else does it change? Is 12 the same? N times t. This is n times t, so it's gonna be n is 12, t is 12. No, n is 4, t is 12. So this is gonna be 4 times 12, right? Which is 48, correct? Let's see how much our interest will change. 15, 7, 48, 58. 15, 7, 43, 58. It increased. Does it make sense? Why are the results different? Sorry, 748, 58. This is 58. Why am I getting more interest, more money? Because it's the same rate. Everything is the same. I'm just getting quarterly interest. Why am I getting more money at the end? This is 15,644. And this is that one, 15,740. Almost $100 more I'm making. Why? Why am I making more money? Yeah, because I wait 3 months, quarter means 3 months, and I'm already getting some interest deposited into my account, and that new money, new interest start making money for me. Another interest is computing over that little interest I got. Instead of waiting 1 year, I'm seeing interest early, getting interest early, and that interest is making me money. And it's small money it's making, but still making a difference over 12 years. So my prediction is monthly interest is gonna earn me more. Even this is gonna be maybe 900 something, 700 instead of 700. Let's see. If it is monthly, what is n? N is 12. This is gonna be 12 years, 12 months. How many? It's 12 times 12, 144. And no, it wasn't a big change. 15,766, only $20 more, and 14 cents. It's still 20 bucks, okay. That's 14. I should have maybe entered this. $743.58. I mean, if you make a small mistake, I think it's gonna say incorrect, so make sure you double check your work, okay? And n was here 3, and let me know if you see a mistake in my moves, okay? Alright, n is 365 now, 365. This is gonna be 365, and the top will be Alright, it's gonna be 12 times 12 years of 365. See if Google can do this for us. Yep, 15,712. No, 13. We round up to this 13. How much increase? Only $11 if you take daily. Finally, continuous compounding. For continuous compounding, we change the formula into what? PERT, right? P-E-R-T, which is 10 grand. R is again 0.038 times is 12 years, 0.038 rate. So that's what I'm gonna type in here. Google will understand E. R is 0.038 times 12. Oh, missed. No slash. Okay. 15,777.50. It needs to, the best is continuous, of course. This should be the greatest amount here. Is it really greater than the previous one? Yeah, about 47 cents, 37 cents, but still a difference. Imagine you're investing $10 billion. You're a CEO of Apple, for example. You have $10 billion. This 37 cents will be $37 million. Okay? I mean, it's gonna be a huge difference. You can pay off your salary with that. Alright, I'm scared to check the answer. Because if I make one mistake, I think it's gonna say the whole thing is incorrect. But, so double check, yeah. Where did we mess up?
Oh, I see. The quarter is 4. It's not.
Oh, okay. Yeah, thank you. I hope that's the only mistake. Oh yeah, there you go. It's a big relief. Just one digit wrong, yeah, your whole work is trashed, so be really careful. But you have calculators, right? And in case you don't, use Google, so you don't have to do any hand calculation here. Alright, that was interest questions. Interesting, right? Interest questions, okay. Alright, next time, I'm not sure we can start this. We're gonna take a look at another area we use exponential functions. It's actually nuclear materials, radioactive materials, and this is really true. Do you know the Russian guy Alexander Litvinenko, whatever, how do you pronounce it? In 2006, they found remains of this material in his blood. He's been poisoned by this material. Okay, and how did they discover he was poisoned and when? By this calculation. Okay, so it's coming next.